Welcome, Dr. Mojtaba. Can you start your literature now?
Thank you very much. Just a minute. Hello, everybody. Thank you for your attention. Today, I want to talk with you about a very interesting topic which directly relates to our lives. Earthquake and earthquake early warning system. The topic of my presentation is an introduction to Tehran earthquake early warning system. I'm Mojtaba Namvaran, postdoctoral associate of seismology in Earthquake Research Center of Ferdowsi, University of Mashhad. My presentation consisted of eight main topics, including what happens after an earthquake, Iran and earthquake-prone region, Tehran historical and instrumental seismicity, earthquake early warning system, pioneers countries in earthquake early warning system, Tehran earthquake early warning system, Tehran earthquake early warning system calculation system, and finally, the warning client. The main question is what happened after an earthquake, or in other words, what's an earthquake? An earthquake is what happened when two blocks of the earth suddenly slip past one another. The surface where they slip is called the fault, or in other words, the fault plane. The location below the Earth's surface where the earthquake starts is called the hypocenter, and the location directly above it on the surface of the Earth is called the epicenter. The tectonic plates that make up the Earth's crust are moving constantly as the edge of these plates slide against each other in fault zone. Friction can slow them down, leading to the build of the pressure over long periods of time. When the forces of movement finally overcome the friction, sections of the crust suddenly break and releasing the energy in the form of seismic wave in all directions. I mean, when an earthquake happens, the seismic wave, including the energy, is propagating in all directions, and part of them is arriving to the surface. Most of the destructive earthquakes are occurring in the plate boundaries, as we see here. In this figure, the colorful circles schematically display the earthquake location, while the size of them support the event size. Most of the huge events occurred in subduction zones, but the event's distribution clearly indicates that the Middle East that we live in it is also one of the earthquake-prone regions in the world. After working on the maps for more than 10 years, the scientists realized that 16 countries account for most of the deaths and destruction by earthquakes. They calculated that seismic events cost us about $40 billion globally every year. This amount of damage forced the scientists to find a procedure to decrease the penalty due to forthcoming earthquakes. In other words, as we see in this figure, the distribution of events show that most of the region in the Middle East is affected by the earthquake. So we forced to find a method, system, or something else to protect us against the penalties of the earthquake. Because of the damage due to an earthquake is very high. Iran, an earthquake-prone region. Iran is one of the most seismically active countries in the world been crossed by several major faults that cover at least 90% of the country, as we see in this video. As a result, earthquakes in Iran occur often and are destructive. The Iranian plateau is subject to the most type of tectonic activity. I mean, including active faulting, and also volcanic eruption. It is well known for the long history of tragic earthquake activity in Iran. Not only have these earthquakes killed thousands, but they have also led us to waste of valuable natural resources. Since 1900, the last 126,000 fatalities have resulted from earthquake in Iran, as we see in the list, the left panel. In addition, the Iranian plate is bordered by the Indian plate to the southeast and the Eurasian plate to the north, and the Arabian plate to the south and west, where the Iraq is located on it. In the left panel, we can find the main destructive earthquake which happened during the time in Iran. If we have a take a look on this list, we can find that in each earthquake we have a lot of fatalities, and consequently we have a lot of damage to constructions, and we need to pay a lot for these penalties. Take a look on this figure. In this figure, in the right panel, we can see the Tehran, the capital of Iran, and the left panel is the list of main earthquakes which affect the Tehran in 200 years, in the last 200 years. I mean, if we take a look on the right figure, the megacity of Tehran, the political, economic, and military center of Iran, is exposed to a risk of large magnitude earthquake originating on several adjacent and inner city active faults. I mean, if we can see in this figure, there are a lot of faults which surround the Tehran from the north, from the south, and from the all around. In other words, it has been trapped. Tehran is trapped between a lot of active faults. The city of Tehran lies at the southern border of the central Alborz mountain, which frame the South Caspian basin and have been the source of damaging historical lateral strike slip and reverse fault. The most recent destructive earthquake in Alborz was root bar. If you take a look at this figure, the root bar is located almost here. The root body was the left slip strike earthquake with magnitude of 7.3, which happened on 20 June 1990, northwest of Tehran. This destructive earthquake, taking more than 40,000 lives and destroying 3 main cities around the epicenter. This earthquake was in a seismic gap, and its source fault didn't show clear geomorphic sign of being active prior to the earthquake. East of Tehran, another earthquake which happened around Tehran was happened east of Tehran on 867 in Damban. Its magnitude was about 7.9, which estimated loses more than 40,000 lives.
Excuse me, Professor.
Yeah.
I'm sorry, your voice is not clear. Please, I
sorry.
suggest you reconnect in the internet.
Yes, of course.
Thank you very much. I'm sorry. Thank you.
Excuse me, everybody hear me?
Yes, yes.
Oh,
It's all right now. Okay, thank you very much.
thank you very much. I continue. Okay, I was here. Excuse me for the quality of my sound. I go on. Scientists' re-evaluation of historical and structural evidences reduces estimate of both magnitude and lows similar to 1990 root bar earthquake. The last earthquake to affect the Tehran, the present Tehran metropolitan area, was the Laos Anat earthquake on the central section of the Mosha fault on 1830, with epicenter located almost 30 kilometers northeast of the city, somewhere here. Its magnitude was about 7 to 7.4. It's very, very huge and destructive earthquake. As we see in this figure, there are a few main faults on the north and also south of Tehran. In the south, the main fault is Ray. You can find it here, which caused a lot of historical destructive earthquake, as mentioned in table, left panel. On the other hand, in the north, Mosha and North Tehran fault are too close to Tehran. You can find the Mosha here and North Tehran fault here on this figure. All these seismological and geological evidences highlight the priority of system or mechanism to stand against forthcoming earthquake. Maybe the most important tool to resist against earthquake is to improve our constructions method. But parallel to it, it can be useful to present a mechanism to alarm sensitive points in Tehran as a target zone exactly after an earthquake. Earthquake early warning system generally can be useful tool for reducing earthquake hazard if cities are favorably located with respect to earthquake source and their citizens are properly trained to respond to earthquake warning system. The physical basis for earthquake early warning system is well understood, namely destructive S and surface wave travel at about half the speed at the P wave, and seismic wave travel at much slower speed than signal transmitted by telephone or radio. I will be describing. Okay. In other words, in seismological perspective, after each earthquake happen, three group of waves are started to run from the source toward the surface. The primary wave we call P wave. I highlighted it here. The secondary wave, the S wave, it's here, and the surface wave. The P wave, according to its particle motion, the P wave, according to its particle motion, is propagating in velocity about 6 kilometer per second. Its velocity is faster than other waves, but has no significant amplitude and therefore has no destruction. The second wave is the S wave, which is propagating in velocity about 3 kilometers per second, almost half of the P wave, but with a significant wave, but it has a very significant wave amplitude as we see in this figure. In all earthquakes, the S wave is destructive wave. So the difference in propagation velocity, as I described here, let us to diagnose the earthquake and set us the warning prior the S wave arriving. I mean the difference between the arriving of P and S waves called the lead time can help us to find a time to warn, for example, the target zone for a specific clients. In other words, the lead time is difference time between the receiving the P wave at the first station and arriving the S wave to target zone. Here is target zone is Tehran. This is the fundamental description of the earthquake early warning system. To design an earthquake early warning system, we need to plant seismic sensors, including seismometer or accelerometer, near the earthquake sources. These sensors detect the incoming wave and send a specific parameter to the server, and finally, the server make a decision to send a warning or not. Take a look on this figure here. Generally, an earthquake early warning system consists of 4 main sections, as we see here. The monitoring system, the communication system, the calculation system, and finally the decision system. The monitoring system consists of seismic stations which mostly located on active faults around a study area. The communication system, the second one, is transferring the waveform and warning message in real-time condition. The main difference, it's very important, notice that the main difference between common seismic networks, as we can find in Iran, and earthquake early warning system is the real-time dependency. I mean, the earthquake early warning system should work on real time. We have a waste time. I mean, the earthquake early warning system, in earthquake early warning system, time is the most important parameter. So we should be able to send the necessary information and parameters real time. The calculation system, the third one, consists of 2 main stages. The calculation in the sensor, which we call sensor side or station side operation. I mean, we have 2 different kind of calculation or operation. Part of calculation will have been done on a sensor, and the other part will have been done on the server. The last section of an earthquake early warning system is the decision system, which recognizes that a warning is true or false. Take a look on this figure. This figure indicates the countries that are working on earthquake early warning system. At least 8, I emphasize 8 countries have earthquake early warning system in operation. The Japan, the Mexico, the USA, the South Korea, the Taiwan, the India, the Turkey, and the Romania. Between these countries, just Mexico, Japan, and Taiwan, and South Korea, as depicted in this color, are sending the alert to the public, while the others, like for example the United States, the Turkey, the India, and some country else, are sending the alert to selected users, not sending to all, to the public. These systems can provide a few seconds to several tens of seconds of warning for large earthquake. With recent emphasis on real-time seismology, operators of many regional and local seismic networks are now upgrading their system to reduce the time for issuing an earthquake notice from several minutes to under a minute, thus potentially making earthquake early warning a technical possibility. There is a very important notice that the geological condition of Iran is completely different from the other countries like Turkey, like Romania, like Italy, and other countries. So the lead time, the time that we have for send the warning in each country, it directly and completely depend on time, on the geological structure of that specific country. More significantly, a properly upgraded seismic network can provide a shake map within minutes after a huge earthquake. From an earthquake can be quickly assessed to aid disaster response and recovery. From 2014, we start in Iran, concentrating on Tehran, to design and implement an earthquake early warning system. The first phase of this system was operated in cooperation of JICA, Japanese International Cooperation Agency, started with 4 seismic stations. I selected them in this figure. These 4 stations were covered the eastern segment of Mojtaba. In this section, concentrating on Tehran in cooperation with the JICA, we implemented 4 stations which focused on Mojtaba in the northeast of Tehran. In the last year, through the second phase, we added 22 more stations, and at the moment we have 26 active live seismic stations, which monitoring, recording, and calculating seismic events at the moment. This distribution of seismic stations, as you see in this figure, all around the Tehran, is covering the Tehran, and the number of the stations will be increased to 15 until the next year. This figure shows the instruments which are used in each seismic station. Each seismic station consists of sensors, as you see here. As you see here in the right panel, the sensors, the digitizers, this one is digitizer, the GPS, this one is the GPS, the modem or the communication route, and other electrical devices. The sensors and digitizers are manufactured by Geosic, a famous seismological devices company in Switzerland. As we see in the right panel, here in the right panel, the sensors are inserted below the surface, considering all site selection criteria. Let's come back to calculation system of our earthquake early warning system. The main parameters that should be obtained in earthquake early warning system rapidly are the time of earthquake occurrence. The second one is the location of earthquake, and the last one is the magnitude of earthquake. The time required to detect and issue a warning for an specific earthquake depends on several factors. The first one is, as you see here, is the distance between the earthquake source and the closest seismic network seismic station. It takes a finite amount of time for the first seismic waves to travel from the source to the seismic station. I mean, the closer the station is to where an earthquake begins, the more rapidly the earthquake can be detected. Accurate detection often depends on multiple ground motion measurements from more than one station. So increasing the density is very important. Increasing the density of seismic station, seismic sensors near the faults can improve the detection time. The second one is transfer, as you see here. The transfer of information to regional network. Data from multiple stations is collected and analyzed by regional seismic networks, so ground motion information must be transferred from the station to the processing center. Existing networks use a variety of methods to send data back to the server, improve robustness, including, for example, the radio link, the phone line, the public-private internet, and the satellite link. In Tehran earthquake early warning system, we use the modem and also the satellite link for transferring the data and information to the server. In addition, delays from packaging and sending the data from the station must be minimized to provide useful warning time. The third one is the detection and characterization of an earthquake. Ground motion records received from the station in real time are used to detect an earthquake and rapidly determine an initial location and magnitude of the event. We are developing multiple algorithms for estimating the earthquake information as rapidly as possible. Earthquake can continue to grow inside over many seconds, so magnitude estimate can also change through time as evolving earthquake is tracked. And finally, the last section is the shaking intensity threshold used to issue an alert. Alerts are issued for a region when where the expected ground shaking intensity is above minimum threshold. I mean, alert can be provided more quickly for low threshold of ground shaking because the system doesn't need to wait for a long time after an earthquake. And let's check one of our output for an specific event. This earthquake located in Damavand on 18 December 2020 with magnitude about 3.9. We record this event and did all the calculation real time, and finally the figure showed rising of the waveform to each station. In order to distance, as we see here, the fourth station, the LAR, is the fourth station that detected the wave, detected the event, detected the P wave after 3.98 seconds after the earthquake occurrence. I mean, exactly when the earthquake occurred, the IMZ, the RDS, the DMV, and finally the LAR stations, in order to distance, detected the event and started to calculate. Finally, after 2.98 seconds after the earthquake occurrence, the calculation was finished. Rapidly, our system, after receiving the event, our system starts to calculate the location and magnitude of earthquake using the first 2 seconds of the waveform. In this figure, we can see the distribution of our seismic station in green color. And the Damavand earthquake happened somewhere here, but we don't know where is the location, the exact location of the earthquake. In this figure, the estimated location of an event is depicted with yellow star here. The blue star is the precise location of the event which calculated by other Iranian seismic networks. The figure clearly shows the accuracy and reliability of our system. I mean, the blue one is the location of Damavand station, which was located by Iranian Seismological Center. But the yellow one is the location of earthquake, which was calculated by our network. And finally, the warning time. I described in previous slides the warning time. The warning time means the time that we have after a specific earthquake to warn to a specific client after a specific earthquake. The warning time is calculated for each point through the target zone. For example, if an earthquake like Damavand exactly here happened exactly here, located here, the warning time for the border, initial border of Tehran is something about 10 seconds, but for the center of Tehran is increasing and reach to about 15 seconds, 17 seconds, and finally to the end of Tehran it reached to about 25 seconds. So we have something about 10 seconds to 25 seconds to alarm to specific clients. And finally, we warn our clients or something like this. For example, after finalizing the Tehran earthquake early warning system, we can send the warning to specific clients like Tehran Fire Department, Tehran Suburban Railway, Tehran Gas Department, Tehran Atomic Reactor, Tehran International Airport, and finally Tehran all refinery or any other client that like to receive our warning. Thank you very much, and thank you everybody for your kind attention. I'm ready to answer your question or any other. Thank you very much. Is there any question?
Yes, Dr. Mojtaba, thank you for your good presentation. It's really informative. My name is Wathik Abdul Nabi. I'm a seismologist in University of Basrah Geology Department, and this is really interesting subject for us. And in fact, we don't have this kind of warning in Iraq, so it's for us it's really new things. Actually, the sound wasn't clear enough to follow up all the details, but the slides were very clear, so we were able to understand the subjects. But however, we have, I'm sure, me and other audiences have many questions. I think we have time for questions. My question is what is the average time between the earthquakes origin time and the warning? Is there an average time that we can get? This is my first question.
Okay. Okay. Thanks for your kind attention and question. I think you are Dr. Wathik Abdul Nabi. Yeah, I'm right.
Yes. Yes.
Yeah, I think I follow you up your paper. I think so. Yeah.
Yeah, that's nice of you. Yeah, I'm glad to hear that.
Thank you very much. For your question, you asked me the average time for the warning. It depends on different factors. For example, it depends on the location of the earthquake, and specifically depend on the velocity model of the study area. It's not dependent on the magnitude of the earthquake. For example, if we see here, it's the location of an earthquake. If an earthquake occurred here, exactly on the, for example, east of Tehran, we have a few seconds after an earthquake to arrive the P and S wave to the Tehran. So specifically and directly, the lead time, the warning time, is depending on the location of the earthquake, and the second parameter is the velocity model of the study area.
So as I understand, you said a few seconds.
Yeah, it depends on the mainly depends on the distance between the epicenter, for example, is here, and the target zone. For example, in here we can find that the distance between the epicenter and the target zone is something about 50 kilometers, more or less. So the propagation velocity propagation of the S wave is something like about 3 to 3.5 second, 3.5 kilometer per second. So we have about 20 for the middle of the 20 seconds for the middle of the Tehran.
And I mean, for people, these few seconds are not enough to do any
Yes,
reaction, right? But
yes,
it's important for like the subways, for example, trains, and for the airports.
yes, of
Am I
course.
right?
Uh, Another important point is that the geological structure of the study area. For example, if we have a take a look on the Mexico has a very famous and old earthquake early warning system, one of the most famous earthquake early warning systems in the world. And the geological structure of the Mexico is a subduction zone. And also the location of most of earthquake are far from the Mexico City. It's for example. So for example, the lead time, the warning time for the Mexico is so more than for example Tehran. For example, the Mexico City has I think about 60 seconds to send the warning. If we take a look on this figure, sorry, if we have take a look on this figure, the Mexico City is here, and also the Japan is here. Both of these countries are affected by the subduction zone in geological perspective. So the events are so deeper than earthquake for example, are deeper than earthquake that happen in Iran or Iraq. Because the earthquake in Iran are very shallow, like Iraq, so the time for warning is less. And also, we have two kind of alert for the earthquake early warning system, as we see here. For example, few countries like Mexico and Japan sent the alert to the public because they have more time than the other countries. But for example, the Iran maybe, or the United States, and also maybe in the future the Italy will send the alert to the selected users because the alert time is less than the countries like Japan or Mexico. I hope to answer your question correctly.
Sure. Yeah, it's very clear. Yes, yeah, I really appreciate your answer. Yeah, thank you
Thank you
for
very much.
the explanation. Actually, I have more questions, but I let my colleagues who are attending your presentation to ask questions. Thank you, and I really hope to keep in contact. Actually, I looked up for your email. I found it on one of your papers, so I would like to contact you if you don't mind.
Thank you very much, and I'm very happy to talk with you, Professor Abdel
Thank
Hadi.
you. Thank you so much, Doctor. I think Ali Ramthan may ask a question. I think he has a question. Also, Muntalar and Dania, I know they are interested in seismology. So if they have any question.
Thank you, Dr. Mojtaba. I have one question. I want to understand how deal with the velocity model inside the warning system.
Can you describe more? Excuse me, Professor. Can you describe more your question?
The velocity model difference from area to another. How deal the velocity model inside the warning system?
Okay. For example, I think there is a lot of similarity, maybe in some kinds, between the velocity model of in Iran and Iraq. But for example, in Iran, we have a different geological structure. For example, near the Tehran, there is the Alborz structure, Alborz mountain structure, and maybe in the south of Iran, we have, for example, the central Iranian plateau, or in west of Iran, like Iraq, we have the mountainous region like Zagros. In each section, in each geological structure, we have a specific velocity model. In the velocity model, specifically on the first 50 kilometers, we have different model for the arriving of the P wave and the S wave. Therefore, if the velocity model varied for the arriving time for the P and S wave, the lead time, I mean the difference between arriving the P wave and the S wave will be varied. I mean, can I show you a figure? Here. For example, take a look on this figure. The P wave arrived, for example, in 0.5 seconds. But if the velocity model varied, for example, in other geological structure, the arriving time for the P wave will be varied. And also, we have the same condition for the S wave. So, difference between the P wave and the S wave will be varied, and the lead time, I mean the warning time for a specific event, will be differentiated between two geological conditions. I hope to answer your question correctly.
Yes, thank you, Doctor. Thank you.
You're welcome.
Excuse me, Doctor. I would like to ask more another question. Regards to the instrument and cost that we have or we need to have to do the early warning system. For example, what type of instrument is the best or the better? Like in Iraq, we use GRAB systems for seismometers. Is there any specific kind, and also for the transferring the warning, for example? So what type? I think you mentioned the type that you are using in Tehran.
Yes, of course. About your question, we have different type of seismometer and digitizers, but the main point is that the type of for the sensors and digitizer, if they should be the real time. I mean, for example, we have a lot of countries that are manufacturing the sensors and digitizers. For example, we are using the geosync sensors and digitizers, but there are a lot of other countries like Bural. It's a very famous country, very famous manufacturer company. But the main notice about using sensors and digitizers, specifically digitizers, can be used in the earthquake early warning system is that they should be real time. I mean, the real time mean that they should be able to send the waveform on a real time, because most of the digitizers have a delay on sending the information, on sending the waveform. So we waste the time and we cannot use them in earthquake warning system, because in the earthquake early warning system, our warning are depending on a few seconds. So the main aspect, so the main point that we should emphasize for the digitizers that we use, it should be the real time. It's a keyword for the digitizers.
Real time, is it based on a satellite connection or internet connection?
None of them. The real time mean none of them. I mean digitizing. I mean, for example, in the sensor, we have the, for example, the velocity or the the velocity meter or the accelerometer, digitizing of the voltage into the digit should be in real time. I mean, before transferring the waveform. I mean, digiting the waveform should be done in real time. Because most of the sensors and digitizers are not real time. For example, it takes a few seconds after receiving the waveform to digit them. But in the for example, in geosync sensors or for example in Coral minimum sensors, the digiting of the waveform have been done in a real time. There is no time between receiving the waveform and digiting them in the digitizers.
Yeah, I didn't get the I know real time means to get the to receive the waveform exactly when it happened, but
Yes.
which how is going to move from the digitizer to the receiver in Tehran, for the center in
Okay.
Tehran?
This is another point. For example, if we have a real-time digitizer, so we have no time for digiting the signals, we have another, for example, delay time in sending the information into Tehran, into server, for the calculation and making a decision. It depends on the communication system. At the moment, we have two parallel communication systems in Tehran. First of all is the modem communication basement. It's based on the TDLE internet connection. And the second one is the satellite, satellite instrument that will send the information and waveform to the server. Most generally, on the average, the delay between between sending the information from the sensors and receiving them in the servers in something less than half of a second.
How many seconds? I didn't hear.
It's about half of a second, 0.5 seconds.
Oh.
Less than 0.5 seconds.
So which one are you using for the warning system?
At the moment, both of the, for example, both of the methods are working properly. Are working parallel to each other. Because, for example, if an earthquake happen, maybe the if which one of them distracted, we have an alternate method to transfer the information to preserve the missing the data. I mean, at the moment we are using the satellite, but if the satellite was, for example, ignored or distracted or something else, the second method, the modem, the TDLE basement will be started to run.
And I think the satellite connection is faster than the modem.
Of course. Yes, of course, because the modem is not a reliable method than the satellite.
Yeah, thank you. Yeah, for me, I'm done. I don't know if Hassanian is joining us. I think yeah, he was joining us here. I'm not sure if he left for some reason. Dr. Hassanian is from the Iraqi network center. And in Baghdad, he's really interesting in this presentation, but I think he left for some reason, maybe the internet connection. I know.
I'm ready to answer all of the questions, maybe after the seminar after the presentation by the email, by the
Sure.
WhatsApp or something else. I'm ready to answer all of your
Sure.
questions and
Yeah.
keep
Yeah.
on the connection between us.
I'm going to write my email here in comments, and I really would like to keep in touch.
Thank you very much. I'm so glad.
Thank you. I really appreciate your time and your efforts. Thanks a lot.
Thank you very much.
Dr. Mojtaba, I'm sorry. Do you mean the broadband seismic station cannot be used in this system, or any specific station that can't be used?
I should describe it more, I think. Thank you for your kind question. At the moment, we are using the accelerometer in our earthquake early warning system.
Okay.
But generally, for example, in our Iranian Seismological Center, that we have a very wide seismic network, we are using for example, the accelerometer and also the seismometer. Most of the accelerometer and seismometer, as I described here, are not real time. So we cannot use the data that are recorded in the broadband seismic station in earthquake early warning system. But some type of the sensors and digitizers that have been made by, for example, the Gural company, can be used in early warning system. For example, the digitizers called Minimus are the most famous digitizers that we can use in earthquake early warning system. I mean, if you have a broadband sensor in Iraq, you can use the Minimus digitizers. They are very common and cheap than other digitizers, and we are using them in Iran. And you can use the Minimus digitizer to make the records real time, and therefore you can use the waveform in early warning system in Iran or Iraq or somewhere else.
Thank you very much.
You're welcome. Professor Abdelnabi?
Yeah, I think we are done here. I was hoping to invest our time because we still have 30 minutes left from the presentation. But I guess there are no more questions. So thanks a lot for your time, and it was really nice to meet you through the internet connection, and maybe yeah, this is part of the corona benefit.
Thank you very much, Professor Abdelnabi. I'm so glad that you invite me in this nice meeting. A specific thanks to Basrah University for joining us in this meeting, and also thanks to Firdaus University.
Yeah,
and I hope to coming joint cooperation between Mashhad University and also Basra University. Thank you very much.
Sure, sure. And I really grateful and thankful for our people who worked on this to arrange this presentation and let us meet through webinar. So I thank all of them. Thanks a lot. And have a rest of day. Nice rest of day.
You too. Have a good day for you and for all the other audience. Thank you very much.
Thank you. مع السلامة.
Thank you very much. Assalamu alaikum.